Chapter 6, Section 1. So now we're going to calculate probabilities using the normal distribution. So we did the empirical rule in the prior chapters, right? So you get the bell curve, right? So this is the bell curve here, otherwise known as the normal curve, which was just created by Carl Gauss. He figured out the equation. So the equation for this curve, this bell curve, is right here. There are two variations of it, depending on which book you pick up. They're algebraically equivalent. It just depends which book you pick up as to which algebraic version they give you. It's just a matter of distribution, essentially. So essentially, this is the mean right here, okay? And then it obviously deviates in either direction, you know what I'm saying? So deviation and deviation, okay? Which is what the formula is using. It's using deviation, mean, and then the Euler's number E, basically. Okay, so Gauss figured it out in the 1700s. It might have been the 1800s. I'm not really sure. Somewhere in there, basically. Okay. All right. So let's say we have some data of adult men's heights. Right. So I'm going to take this data real quick and put it into a spreadsheet. This is an example. So I'll paste that there. Right. So whenever I paste into a spreadsheet, I always make sure that I choose a this is the regular option, and there's a no formatting option. I don't want all the formatting, you know what I'm saying, so just get rid of that. Okay, so I'm just going to do this real quick. You don't need to do this yourself, just watch along and take the answer. Okay, so I have all the data here. These are all the men's heights. Looks like there's 40 of them, right? So the two things I need, whoa, that was a bit big, is the mean and the standard deviation. Okay. Take those, shove them to the right. Alright, so we're going to add up all of them from A1 to A40, I believe, right? Right, A1 to A40. Yes. And divided by the 40 values, so there's my mean. And then standard deviation dot, you notice there's population and sample. This is obviously a sample because this is not every single height of men across the entire world, so it's definitely a sample, right? It's A1 to A40. And there's our standard deviation. So 176.4 and 6.01-ish, right? So if I'm going to make the equation for the curve, essentially, I would get this, right? So we're going to say, come on, pen, you're killing me. Come on, there we go, 176.47, that was exact, and this one is 6.01 dot dot dot, it keeps going, right? So our equation is E, right, Euler's number, to the power of, and it's going to be a ratio, so it's negative x minus 176.47, right? Square that, and then on the bottom, we're going to get 2 times 6.01 squared, right? And then this whole thing is divided by 6.01 times the square root of 2 pi. Okay? And that'll give us this equation right here, essentially, right? So let me just copy this over real quick. So essentially I want to copy this to this. There we go. All right, so if I graph this equation, or this function, is this line right here, right? Okay, which is specific. Notice it's a bell curve, right? And it's specific to this data, which is men's height, right? So the middle of it, right? The middle of it, right here, is the mean, which is about 176.47, right? And it deviates by this much, plus or minus, you know, for the deviations. So the total area under the curve, area, is 1, right? And which is also probability, right? So essentially what we're going to do is calculus without doing calculus. So if we do the integral, right, from A to B, whatever the case may be, so if I go from like here to here, right, if I'm doing calculus, the area under here is the integral of that function, essentially. So the computer will do this for us, though, right? So in calculus, you're calculating area, but for the sake of statistics, this area is probability of something, whatever the thing is we're doing, essentially. So in this case, it'd be the probability of a man being selected that has one of these heights, essentially. Okay, All right, so let's go to the next page. All right, so then you have to understand normal versus standard normal. Okay, so if you don't have the original standard deviation and mean of the data, right, you use standard normal, okay, which is 0 is your mean, right, and your variance or standard deviation is 1 essentially. So that's standard normal. So the letter used for standard normal is Z essentially, right? So you standardized it. Otherwise, it's X, where X could be the men's height or IQ or whatever the data is essentially you're doing. If you standardize it, it becomes Z. So Z is the letter they use basically. Okay, so you can watch this video here about PDF and CDF. So the sense for probability density function and cumulative density function. So the probability density function, there are many of them, right? So the one that's specific to this bell curve we just did on the other page, right? So there are many PDF functions, right? Because again, you can have skewed data too, or you can have skewed data to the right, skewed data to the left, you know what I'm saying? So there are other ones that are not the bell curve, you know what I'm saying? We'll be doing some of those in later chapters, but this actual curve right here is a PDF function, which on the other one. If I want to calculate the area, right? That's a matter of doing CDF, which is cumulating all the area left to right, which is how calculus works. So if you've taken calculus before, you understand that the integration process calculates area left to right. Okay, so we want the probability, because again, in calculus it's area, but for us this area is probability essentially. Okay, all right, so the z-score breakup of the normal curve is the same as the empirical rule. There is no difference, right? This is one deviation above, one deviation below. This is one z-value, negative one z-value, right? It's the same breakdown percentage-wise, and the area is 1 either way for the whole bell curve. The only thing that changes, of course, is if you're doing z, the center is 0, right? If you're doing x, right, then this is whatever the value was, like 176 or whatever the data happens to actually be, essentially. Okay? All right. So if we want to standardize a score to figure out where it lies in a data set, you do a z-score. So z-score and standard score are the same thing. Okay? It's their distance from the mean, essentially. Right? And what you typically say is if you're between -2 and 2 z-score, which is plus or minus 2 deviations, that's 95% of the data. That's pretty ordinary. If you're less than -2 or more than 2, that's the upper and lower 5%, right? So if you're looking at a bell curve, right? Let's go up here, right? 95% of your data is in here, correct? So that means the other 5% is here and here, 2.5 here and 2.5 here, approximately, essentially, right? Okay. So end of the day, z-score is, your distance from the mean, essentially. So don't think standardized score and z-score are somehow different things. Z is just the letter that you're using to describe the x value, right? Because it's either x or it's a z, essentially, or x is the actual data value and z is the standardized score, okay? If you think about what the formula is, the formula essentially is, right, the actual value, right, the individual value, versus the expected value, which is the mean, divided by the standard deviation. So that gives you your relative position, essentially. Okay? Okay. All right, next page 3. So let's say we take the weight of women here. So we have person A. Oops. Come on, person A. I think my pen to work here. There we go. Person A and person B. Okay. So z-score, right, minus z-score minus. Okay, so the average is 134.7. 134.7. It deviates by this. That's just 10.7. 10.7. Right, person A weighs 120 pounds. So that means it's going to be a negative z-score. Person B is 165 pounds, so 165 minus that is a positive value. So that's going to be negative 1.37 ... This will be 2.83 ... Okay. So basically, this is between 2 and -2, so this is within normal range. This is beyond 2 or -2, so that's not within normal range, right? So this person below average weight, this one person's above average weight, but this one's too far above average weight, essentially. Okay, so that's how you can tell using z-score how something relates to an entire group, essentially. So and this is comparative within the same group. You can do different groups comparative also. Okay, so let's look also at blood pressure, right? Let's say we do blood pressure, right? We have person A and person B, right? Person A, person B. So z equals minus, and z equals minus. Okay, so the average is 67.3. Okay, let's get your heartbeat, I guess. BPM, not blood pressure. Okay. So 60. So we'll assume that these are at rest and you didn't go running or something like that. Okay. Standard deviation is 10.3. Okay. Okay. Notice the calculation is the same whether it's population or sample. Okay. Person A is 48. So this person will have a negative z-score because their heartbeat is below average, and 101, so that's pretty high. I'm going to assume they're eating too much Haagen-Dazs there, right? So that'll be a positive z-value. All right, so that'll be negative 1.87 dot dot dot. This one will be 3.27 dot dot dot. So what is the case here? This person is clearly not in the ordinary range. This is not healthy because it's way above normal, right? This one is within normal range, right? So that is healthy because it gets between 2 and -2. This person's probably a runner, so they have a naturally low heartbeat, you know what I'm saying? Resting heartbeats, if you do a lot of athletics, that tends to be the case. But if you're extremely out of shape, you know what I'm saying, then you'll have above average. Okay? Okay, so common symbolism that's used in this book and many other books is this here. Okay, so this is saying the data value is X, and I don't know what those data values are. They could be heartbeats, they could be the men's height, they could be weight, IQ, they could be anything, right? Is approximately normal, right? So if I see the data value is approximately normal, that means I'm doing the bell curve, right, with Z essentially. That's what that tells me. Because is everything normal? No, we know data can be skewed left or skewed right, right? It doesn't have to be normal. Also, it can be uniform. There's a few others. So if I see that N right there, I know I'm supposed to use the bell curve essentially, right? And that is the mean, right? That's the mean. And that is the standard deviation essentially. That's how you read that symbolism essentially, right? Is the idea. Okay. All right. So that's commonly used, so they do just kind of a shorthand to save a little bit of room here. Okay, so let's say we have a game with x approximately n 16.4. So that means I can use the z because it's normal, and this is a mean of 16 and a standard deviation of 4, right? So we'll do the z-score here and the z-score here. Okay, minus, so the average is 16 for this game, and it deviates by 4. Okay, so this person scored 10 points. This person scored 20 points. Okay, so that's -6 over 4, which is -1.5, right? And this will be 4 out of 4, which is a +1. So what does this actually mean? So this person scored 1.5 deviations below average. This person scored 1 standard deviation above average, or above the mean essentially. Okay, that's what that essentially means, right? Because z-score is a position, okay, which is related to standard deviation and mean essentially, right? Okay, let's go to the last page here. Alright, so what we've done so far is use z-score to figure out where we are in a group. But we can also use it to test 2 different groups. So let's say I take a calculus and a history test, right? So I'm going to take a calculus test and a history test. So the calculus test and history test are not of equal difficulty. They don't have the same number of points. There's no comparative. So how do I know which one to do better in compared to the class, right? So all 30 of your classmates, whatever the case happen to be, go to one class, take a test, and they go to history, take another test, right? How do you know which one you did better at? So z-score minus and z-score minus. Oops, kind of dipped up there. Okay, so in the calculus test, you score 62. The average mean is 50, and the deviation is 10, right? So it means your class scored an average of 50 with a deviation of 10. In history, you scored a 30. And again, these tests aren't the same number of points. The average is 25, and the deviation is 4, right? So lower average, but less deviation. Higher average, but more deviation, right? All right, so that's 12 out of 10, which is 1.2, and that's 5 out of 4, right? Which is what, 1.25? So the question is, what one did I do better at? So normally a student would look at this in grade school and say, well, I got a 62, that's better than a 30. Yeah, but these aren't the same tests. They're not graded the same way. They're not the same difficulty. They're not the same number of points, right? Relative to the test, this one is better, right? Because you get higher relative position on the history test, essentially. Same thing with SAT. It's not the same SAT every 6 months. They change the SAT, so they have to standardize the score to figure out where you ranked, because you get the same number of questions right the next time. It might actually be a higher or lower score depending on the difficulty of the actual SAT that was given, because they're not all the same every time. Okay, let's say we take a couple different games here and do the same thing, right? So we'll take game A and game B. So two different games, two different scoring systems. We're comparing like baseball to football or something like that, right? So Z equals. These aren't baseball and football, but it's the same general idea. Okay, so person A scored 60 points in game A, and the game is 80 average with a 16 deviation, right? That's approximately normal, so it means we can use Z. Okay, 18 points in game B. Okay, and that game is an average of 20 points and deviates by 3. So in either case, I didn't do very well in either game, so clearly I'm bad at everything here. Okay, but the question is not whether I'm good or bad. That's not very good, -2. Let me fix that. The question is, which one did I do better at? Well, this one is -1.25, right? This one is -0.6 repeating, right? Because 2/3 is 6 repeating. Well, this one is a lot lower negative number than this one, so clearly this one is closer to 0, which would be average. So I did less worse on this one, I guess. Now, that's a great way to say it, but that's really the case, right? So either way, we're bad at these games. We just did less worse at the other one, essentially, right? Okay, so let's say we looked at adult men's weights, and it was 195.6 pounds, right? I think we did height before, right? Now we do weights. Okay, so we want to do the ordinary range using Z. So what's considered ordinary depends on the context. We're doing it in terms of Z. So typically, and again, this is a rule of thumb with Z, it'd be -2 to 2. So that means 195.6 minus 2 times the deviation, which is 20.3 pounds, right? So you can put X or you can put pounds there, whatever you want. I'll put X just for argument's sake, because the book likes to use X for the real data every time, you know what I'm saying? So 195.6 plus 2 times 20.3, right? And just label them as pounds if you're going to do it that way. So option 1 is to put this as pounds instead of X, or you can label them each as pounds, but typically the book puts X, but it's really a preference type of thing. Okay. All right, so that'll give me the range of ordinary, essentially, right? So what I'm missing is the unusual range, right? So the unusual range will be Z is less than -2, or, oh, not Z, not X. What am I doing? What am I doing? z is less than -2 or z is greater than +2, right? So that means z, sorry, not z, x, or x. Okay, x is less than 155 pounds, right? Or x is greater than 236.2 pounds, essentially. Okay, that's essentially what that is. That's the ordinary range, using the perspective of z-score, essentially, right? Okay. So approximately 68% of the data, 95% of the data, and 99.7% of the data lie between two values. How many standard deviations is that? And the values lie between what z-scores? Interesting. Okay. Well, if you think about this, this is the empirical rule, isn't it? It's 1, 2, and 3 standard deviations, correct? Okay. So essentially, we'll look at the first one here. The first one is a range of 1 deviation, right? So it's 50 plus or minus 6, because deviation 6, which is this many points, right? So if I add on to that, that is negative 1 to 1 z-score, right? Okay, that's essentially what we're adding. So that's a 1 deviation or 1 z-score range, essentially, right? Okay, so 95% is 2 standard deviations, right? So we'll paste that in there. So that's 2 deviations. So that's essentially -2 z to +2, right? And then lastly, the 3 deviations, right, would be plus or minus 3 deviations for 99.7% of it. And this is the empirical rule, right? So -3 is less than or equal to z, which is less than or equal to 3. Okay, and again, this all goes back to the empirical rule, which we covered in the prior chapters, which is also right there, right, as far as the percentages of data that fall into the bell curve. And again, everything we're doing here only applies to the bell curve and the bottom of the bell curve, essentially. Right? So the total area is 1, and the bottom of the bell curve is either x or z, depending on what you're doing. Is it standardized, or are you using the actual values? Either way, this axis is either x or z, depending on what you're doing, essentially. Okay, that's the end of this section.